Hi everyone, I'm David Hendricks, and this is my colleague Andrea Barberio. We're both engineers over at Facebook. I am primarily working on firmware these days, and Andrea is a production engineer, and let's get started. So we're going to cover a few topics today. I'll be covering some kind of high-level items, and Andrea is going to dive into the details. So we're going to start with some open source initiatives, the problems we're facing with firmware, and how we're using Linux boot at Facebook. Andrea is going to go into a lot more details about system boot, which is something that we're adding on to Linux boot. And also we'll talk about some of our collaborations and partnerships. So first things first, open source is pretty huge at Facebook. We have a strong community of open source software developers within the company, and we're actively promoting open source software outside the company. We use and contribute back to software projects such as the Linux kernel and CentOS. So we already have a pretty strong systems software development team going on there. We create projects and release them to the open source community. Actually, our moderator was commenting on how he uses React.js at his company, so that's a very popular example. But of course, Facebook isn't just high-level web applications. We're also one of the top contributors on GitHub. And we've actually founded a few initiatives within the industry. The Open Compute Project is a very well-known example, but also the Telecom Infrastructure Project, which we're cooperating with a lot of telecom companies to improve connectivity throughout the world. OCP today is over 100 members strong, and TIP is over 500 members strong. So we've built these really robust communities towards opening up data center hardware and access throughout the world. But there is an important part that's been missing from this story. I mean, we have these great open source hardware initiatives, and we have these open source software initiatives, but there's something in between. And if you were to jump and say, oh, firmware's the missing piece, you'd only be half right. Because in 2015, we released OpenBMC, which you may have heard Sai talk about earlier, well, yesterday. And we've learned a few things along the way about deploying open source firmware in our fleet, and Chris and Samantha will talk more about that later today. So after OpenBMC, with the lessons that we've learned, we believe it's been a big win for us, and opening up the system firmware is the next logical step. So why open source firmware? Well, first let's scope out the problem a little bit. So a lot of people, when they think of a company like Facebook or even Google or these other companies, when they think of the infrastructure, they might think of a closet with some servers in it. And of course, if you saw the Social Network movie a few years back, you might have the impression that Facebook is run off Mark Zuckerberg's computer in his dorm room or something. But this is how Facebook's infrastructure looks. Actually, this is an outdated picture. But this will give you a better idea. There's actually one more data center in Newton, Georgia that's not pictured there, and we just announced that we're building an 11-story tall data center in Singapore. So our infrastructure has grown quite a bit from Mark Zuckerberg's computer in his dorm room to a geographically diverse system of network of data centers. So that's a lot of servers, and it's a lot of switches and a lot of networking gear, and it doesn't stop there. So this is a picture of our first version of the Open Cellular, the product. And so we're working with our partners to build out new communications infrastructure and improve existing communications infrastructure throughout the world. Our mission is to give people the power to build community and bring the world closer together, and that's exactly what we're aiming to do with Open Cellular. Only about half, or well, actually less than half, of the world's population has internet access, and we're working to get more online so they can participate in the community, economies, and be part of the larger community. So with all that said, we have a lot of hardware that we're supporting, multiple generations of servers and switches in our data centers. We have these external projects going on too, and if you're looking at just one server, or one product, you might think, booting's not such a big problem. But when you're looking at it in the broader scope, it turns out booting is pretty hard. For one thing, we have the ever-increasing amount of hardware that we have to support across all of these products. So even things like local booting, just loading your OS image off of some local media device. Again, when you're looking at it from one product's perspective, doesn't seem like such a big deal, but when you want to do it across a whole range of products, you might have you might be booting off an eMMC drive, a SATA drive, NVMe over PCI Express. You might have complex setup. You might have to set up clock trees. You might have to enumerate buses, allocate memory resources, just all this stuff. And all these devices have multiple generations, many chip vendors, many protocols, and getting it all right is a big job. So as a result, firmware has kind of become an operating system in its own right. Firmware these days, it's no longer just a monolithic blob that does one thing. It's an operating system with drivers, protocols, crypto libraries, all kinds of stuff. And because it's grown, it's also become a much more valuable target for attackers. So there's a lot more demands on firmware security. So in addition to all this complex hardware support, we also need to take into consideration things like verified or secure boot, measured or trusted boot, and attestation. And even just provisioning a system. So installing Linux on one machine is pretty easy. Doing it across all those machines in the data centers and then on machines out in the field, sometimes in rural places where if something goes wrong, you're not going to have a technician out there for days to be able to fix it. So it turns out provisioning is hard, and we need something very robust and very reliable that we have total control over and we can debug it. And so that's where we're going with this. So a few problems with the closed firmware that we've noticed is it's archaic, complex, often quite buggy. This isn't necessarily unique to closed source firmwares. Even some of the open firmware implementations out there are often unfamiliar to ordinary developers, and they can be difficult to extend. We want to be reactive instead of, we want to be proactive instead of reactive when we're debugging. So one of the main problems with closed source firmware is oftentimes you wait for a problem to happen and then you react to it. And usually that reaction entails a lot of back and forth with the vendor, trying to describe the problem, hoping they understand. Maybe they have a magical fix, maybe they don't, but there's not a whole lot you can do. So from our standpoint, we want to be able to be proactive. We want to be able to get in there, look at the code, identify exactly what's wrong, build it, and deploy it. Closed source firmware tends to be hard to maintain, we've noticed. You oftentimes end up, especially in an infrastructure like ours, with many generations of servers. They don't all have the same features. You can't forward or backport features easily. And even if it's supposed to be the same specification, we found that sometimes vendors implement things differently. I mean, you have multiple vendors and you have one specification, and it's supposed to be uniform, but they end up implementing it differently, and that causes issues. With the closed source firmware, we have to deal with vendor-specific tools. So a machine coming from one vendor and a machine coming from another vendor might have totally different repair manuals. And there are, of course, many dimensions of supporting firmware at scale that put a huge demand on the robustness, flexibility, and debuggability of the firmware. So at Facebook, a lot of this stuff falls on the sustaining team. That's the team that I'm in. And we recognize that firmware has an impact across the entire product lifecycle. So of course, you need to design your firmware to actually boot your device, and you might need to make necessary changes based on various stages of production you're at. Maybe you decide that you want to swap out an IC, you want to set up your GPIOs a little bit differently, and so on. And being able to modify the code and rapidly release it again helps out with that a lot. Of course, you need to build the thing, and you need to make sure your tools work with whatever the vendor's, the manufacturer's tooling is set up for. You need to test it. To what extent can you test is a big problem for us, because oftentimes it's just black box testing. We really want to get more into the white box testing of firmware. You have to be able to deploy it. So firmware may need to be updated after initial deployment to address bugs that come up. You need to have reliable tools that do not negatively impact operation. And you may also need security mechanisms in place, such as signed updates and a fallback path in case the update fails. We want to be able to design this to work in our infrastructure and in the OpenCellular's case, in our partners' infrastructures, and we need a lot of flexibility to do that. We can't just take something that some vendor dictates to us. And when things go wrong, what do? Open source firmware enables us to be proactive rather than reactive, again, discovering and prioritizing issues quickly so we can put necessary resources toward fixing the issue. And finally, when you have a big infrastructure like ours, you tend to have a lot of machines cycling through. Like, there are power and space constraints, so oftentimes we'll have to decommission, many, many thousands of machines that are older just to make room for newer ones. And the old machines might still be perfectly fine, and they might still run perfectly well. So those machines get bought by companies like IT Renew, who have to also test, deploy, and sustain for their customers as well. So we want to support many generations of equipment. We want feature parity. We want a unified, adaptable toolkit. And we want to support many different use cases, not just data centers. And we need to be familiar and have a low barrier to entry. So here's how we're addressing the problem. This is a diagram we came up with for the Linux boot project. And so we're targeting use of core boot with Linux boot. The Linux boot will contain an init ramfs with uroot, which Ryan talked about. And from there, it's pretty easy. Once you have that Linux kernel up and running, it's pretty easy to download your kernel from the cloud or the network, or get it from a local storage system. Network booting used to mean loading an operating system from a machine across the room. These days, we need to think of it on a global infrastructure, particularly with systems out in the field like with OpenCellular. So we use Linux a lot. We want production quality drivers, networking capabilities, and cryptography. We want the versatility that Linux brings. I mean, you can run Linux on anything from high-end servers to toasters, so it's perfect for us. And we have engineering teams who understand Linux very well. And so we want to leverage that talent that we already have. So it enables us to simplify our sustaining operations, maximize code reuse, share tools, apply processes and best practices uniformly, and just in general have a higher eyeball to code ratio. So for us, Linux boot makes a lot of sense. And more generally, open source firmware enables our organization to have much better insight and control over our firmware and utilize our engineering resources much more effectively. Here are some of the current projects that you can find over at our booth. These are all, so the OpenCellular and OCP platforms listed are in upstream core boot already. So OpenCellular, the Rutundu and Elgam boards, named after mountains of Kenya, are under source mainboard OpenCellular, and the Monolake and Wedge 100S platforms are under source mainboard OCP. And our Linux boot distribution uses uroot with system boot, and Andrea will talk about that.
All right, thank you, David. So my name is Andrea Barberio. I'm not a firmware engineer, not a hardware engineer, but I'm a production engineer, which at Facebook means that I take care of scalability and reliability and performances of the Facebook infrastructure. So let's see how does it fit into firmwares. My team is responsible for the provisioning of the operating systems on the bare metal at Facebook, which means installing, reinstalling, configuring, and automating all the process around this, so we don't do operations manually. The installation of a single operating system on a single machine is a pretty simple task. While doing the same thing at scale, it's pretty complex. There are a lot of moving parts that are involved. There are a lot of network services, components, etc., and the network itself can introduce a lot of noise. To give you an idea what this looks like from my perspective, I'll tell you very quickly what happens from a host side when we try to provision a new machine. The machine powers on either from a cold boot or from a reboot. Then the firmware runs the DHCP v6 client. Our infrastructure entirely IPv6, so that we use DHCP v6. The server responds with a network boot program, with a URL that says, this is what you need to download to do your job. Then the download is done by a TFTP. And again, we are still in firmware space. Once the network boot program is downloaded, the firmware will execute the network boot program, and the installation will start. And we are in software space at this point, and we don't care about it. What's wrong with this? Well, it works most of the time, but as David said, different implementation of closed source firmware can have bugs. DHCP implementations can be buggy, TFTP can be buggy, and so on. And since we also depend on different vendors, we also have different firmware versions, which means we have different standards in quality, in time to respond, in fixing bugs, and so on. And as I said, most of the times these work, but at a large scale, even a small fraction, 1%, less than 1%, can translate into a lot of operations for our teams. So what we need in this case to make our life better is having reliable clients, having better protocols. For example, TFTP is not necessarily the best protocol. It's quite old, literally my age, and it's very slow and unreliable. So we have HTTP and HTTPS. Why not using them? And above all, we want to control the implementation because we run on our servers with a lot of data. We want to know what we run. We don't want to depend on somebody else's code. We don't know what's inside and so on. And we want to be able to find bugs in ourselves, fix them, and deploy as soon as possible. As I said, I work in provisioning. So let's see how does Linux boot fit into provisioning. For us, it can simplify our workflow a lot because we use a Linux kernel with a very stable network stack. It's battle tested and tested by many more eyes than we can have inside one company. We have better DHCP and TFTP implementations than what we can find in other closed source proprietary firmwares. But even better, we can implement whatever protocol we need. For example, in this case, we use HTTPS instead of TFTP, which means we have a lot more bandwidth. We can download bigger images with more reliability in less time, but we can also use high-speed links and distant links efficiently. The other big benefit is that we can run consistent firmwares across the fleet. If you have one hardware type, you will probably run one firmware from one vendor. Then you have upgrades, and multiply this by all the number of hardware types that you have in your fleet. With Linux boot, we can consolidate everything under one single firmware and have only one single code base that runs on our fleet. So we will never duplicate the bugs across different hardware types. And as I already said, above all, that's the most important part for me, is that we control what we run on our hardware. Again, from the provisioning perspective, thanks to the use of Linux boot, we expect to largely reduce net booting failures, which for my team means a lot less operations, a lot more reliability. Other teams will be able to do more things faster and so on. Linux boot is open source, of course, and it's entirely developed open source first and then used internally. And open source, as you, of course, know, means that auditability, debuggability. We can look into the code. We can actually run proper troubleshooting tools. For example, you can run TCP dump in your firmware. We know the security model. It's the security model of Linux and other open source components. So we have insight into how things are actually debugged and developed and fixed. But also portability is a big is an important element because Linux can run on many architectures, which means that the same code base with just different configurations and builds can run on different hardware. For example, David mentioned that OpenCellular is an example of the same code that runs on a completely different architecture for a completely different use from data center hardware. And of course, we can apply, since Linux boot moves the needle from firmware developer to software developer. This means that we can use our software developers, which are largely available compared to firmware developers. We can have more eyes, more people with expertise in that space, and we can also leverage the collaboration from the external community. So all of these are great advantages, but let's see, Linux boot is really versatile. We can do more than just running in firmware. So we had this idea a few months back. Linux boot at Facebook is made by core boot, Linux kernel, uroot, and system boot. So why don't we reuse all of this goodness for other purposes, not just firmware? And as I said, I work in the provisioning team, so I said, why don't we use this for starting the provisioning, to handle the whole provisioning? So we have one single code base for both our firmwares and our provisioning workflows. Benefits of this, of course, are that we have one code base, we fix bugs once, but we also are, the people that are familiar with our firmwares are also familiar with provisioning infrastructure and vice versa. And so we started experimenting multiple projects based on top of uroot and Linux kernel. In this slide, I mentioned two of them. One is called Prov Launcher, developed by one of our interns. It's actually finishing right now. And the other one is called Yard, which is a network installer. The first one is kernel and RAMFS based on uroot, which is pre-provisioned on every machine. And this means that you can use this as a primary boot entry in your machine. So when your machine starts, it does not try anymore to use the firmware, DHCP, and TFTP client, but it will look for a binary on the disk, and this binary with stable tools, with the proper Linux environment, etc., will provision the machine in a more reliable manner. This is already improving the reliability of our infra. On the other side, we also have, in case we can't pre-provision the image, we still need to be able to boot from the regular firmware, and so we created YARD, which stands for yet another RAM disk. Names are hard. So this RAM disk is basically very similar to Perf Launcher. It just serves a slightly different purpose. It's downloaded over the network by the firmware. It's intentionally very small, so it can be downloaded even via TFTP in a decent amount of time, still talking about minutes in the worst case. And this then will trigger the installation of the machine with a proper environment. System boot. I mentioned system boot several times. I guess it's time to explain what it is exactly. It's, as I like to call it, it's a distribution it's a Linux distribution that implements a bootloader. It's done on top of the work of many other people. There's no core boot, not necessarily, but system boot aggregates many components from Linux boot, which can be UEFI or core boot, which then we have the Linux kernel. But above all, it's based on uroot, which Ryan talked about. Uroot, for who didn't follow Ryan's talk, is very high level. It's the RAMFS and RAMFS builder written in Terlingo. System boot adds more components that basically give our distribution, our system, the personality of a bootloader. Why system boot is different from uroot? Well, it's not really different. It's based on top of it and adds more components. The idea is that we created it to give it this bootloader personality, plus implementing tools that not necessarily fit into the more generic uroot. Whatever we implemented is generic enough and stable enough, will go back to uroot. All the rest will stay in system boot. What's inside the package? This slide has basically the laundry list of components that are present at the moment. I will go very quickly through it, but then more details in the next slides. The first two components are netboot and local boot. These are programs that run inside the RAMFS, and their task is to boot the machine either from the network or from local disk. We will see more in detail how. We have what we call a Linux boot VPD library, which is used for non-volatile local storage, similar to what UEFI variables do in UEFI. Then we have a booter's interface. The booter's interface is a way to describe the way you want to boot your machine. So basically, how you want to. This lets you add more features and more methods to your bootloader. We also have a TPM library developed by Philip, and a TPM tool which wraps on top of this library, and eventually a binary called uinit. This is a naming used by root. It requires a binary with this name, which wraps all the logic above and gives this personality of a bootloader. More in detail, netboot is a regular Linux program. You can run it even on your Linux machine. And in firmware, it will be called anytime your bootloader wants to boot from the network. What it does, in short, is it will try to acquire the network configuration via DHCP v6 or Slack. DHCP v4 is coming soon. Then DHCP will return us a URL, HTTP or HTTPS, and this can be downloaded with a proper DHCP client. With a proper HTTP client like wget or Go's HTTP libraries. Once this program is downloaded, we use kexec to actually run the kernel. Local boot is very similar to netboot in the sense that it boots a program via kexec. The difference is where it looks for the program for. It will scan in its default behavior. It will scan all the locally attached disks, which means whatever you configured your kernel to be able to see. It will look for grub configurations. It's kind of a compatibility mode, but it's not necessary. It will look for grub configurations. We'll scan them and find valid boot entries, and we'll try from the first one until it finds one that works. And eventually, we'll kexec into the kernel with appropriate RAMFS and parameters. Alternatively, it's probably a better method. You can specify exactly what you want to boot from where and with which command line. More about this in the next couple of slides. So The library VPD stands for Vital Product Data. It was originally developed at IBM, and it's used for Chrome OS. And basically, we use it as a key value store on the flash chip. It's used for non-volatile storage in a way similar to how UEFI boot manager and boot variables are used. We also use some similar naming for people to be familiar with it. It can be extended since it's generic key value store for us. And if you don't like VPD, for example, because you want to use MVRAM to store your variables, you can very easily swap it out. The interface is very simple. And it's intentionally easy to swap. Now, let's put these three things together, netboot, local boot, and VPD. How do we tell our bootloader, hey, this is what you have to do? We use VPD to store a configuration, which, as you can see, is just a key and a value. Like, for example, the first entry is boot 0000, familiar name for UEFI, but the content is different from other implementations. We decided to use JSON because it's easy to read for humans, and it's easy to parse for machines, and most languages already can speak JSON. And we defined a very simple structure. You basically have to define just your type name and whatever custom logic you want to implement on top of it. The first entry on the left is what you have to store in your flash to say, I want to boot from the network using DHCP v6, and please do DHCP on the interface with this MAC address. On the right, you can see the local boot entries. Those are the same thing. They will just use a different program, local boot. And you can use them either in grub mode or to specify a device UID and path to a kernel that you want to boot from. And all of what I said above is how to boot from a machine and how to specify your boot order. Now let's see how to implement your own booters. You may want to do something more than just net booting or local booting with the simple methods. You may want to even have a policy to decide how to recover from a failed boot or how to verify an image with secure boot, measure boot, and so on. We created also the booters interface, which is very simple, again, intentionally. You only need to define a type name for your booter, like netboot or local boot or whatever boot, and define a boot function with your custom logic. And this custom logic will be picked up once registered into system boot. In order for system boot to pick it up, you have to register it, but you also have to define a JSON format that your program will be able to parse. How this is done is entirely up to you. Another important component in system boot is the TPM library and TPM tool. And this is meant to simplify the interfacing from the user perspective and from program perspective to TPM 1.2 and 2.0. So this high-level library basically lets you interface to both versions in a quite consistent manner, as in they are different, of course, but most of the features are implemented in the same way, and you will transparently speak to TPM 1.2 or 2.0. Philip is the main developer of this library. He has already merged part of the code into the Google's GoTPM. And some of the features that this library implements are handling the ownership of TPMs, sealing and unsealing, pre-calculating PCRs, which is very interesting, but also something that I find very interesting is the dumping the TPM event log, so you know what's going on your machine. TPM tool is just the CLI that wraps on top of this library. If you want to see more, just go to tpmtool.org. So, system boot, how does it look like? I prepared the screenshot and the video. I will use the screenshot in case the video doesn't work. You know what it is?
All right. Demo effect, right?
Yeah.
Let's see here. Okay.
Great. Hopefully it's big enough. It's a video. Okay, so this is an OpenBNC machine that is resetting a Wedge 100S, the same machine that is outside at our booth. This machine has been rebooted electrically, and then we attach to the serial console. As soon as the machine goes on, core boot will start. We are using core boot for silicon initialization, as David said. So we see all the core boot messages. At some point, you will see the Linux kernel messages. And once Linux starts, we see uroot, and then the customization that we call system boot. System boot will try to boot the machine unless you stop it within a few seconds, which I did. Here the machine is trying to net boot, but then I press Control-C to stop the boot. And in this case, we have a familiar environment. For example, here I run ls and IP to see files and network configuration. Eventually, I use local boot, the program that I showed you, and this program will scan through the disks and then eventually exec into our kernel. Fast forward, because the machine takes a while to boot, and you don't want to see systemd especially run. And there it is. The machine is booted and is ready to be used. Almost there. Yep. OK, what's going to happen in the future? We will implement different security models. We want to give you the ability to verify your code, to use signatures. For example, there is the GPGV implementation in your root that can be used for this. Some of these features are already partially implemented. We also want to have a more consistent way of configuring boot configuration, so you can have more information and more customized to your needs. But we also want to be able to boot EFI binaries, and this is also partially implemented. And I guess, David?
Wow, thank you, Andrea. So, in conclusion, Facebook is going big on open source firmware. We believe it's going to improve our boot flow by making it much more robust and using well-tested, well-supported drivers. We're simplifying our boot flow by reusing all these common open source components. And at the same time, we're enabling collaboration inside of Facebook across a variety of teams, firmware engineers, provisioning engineers, kernel engineers, many, many teams. And we're also enabling more collaboration with our external partners, especially those in OCP, such as Google and 9-Element Cybersecurity and 2 Sigma and IT Renew. And we're even working with Microsoft on the parts of the open source firmware stack that aren't specific to Linux boot. So definitely get involved with the OCP, Open System Firmware effort, whether or not you use Linux as your bootloader. We're also working to improve the state of UEFI booting, along with Vincent Zimmer back there. And lastly, so for us, this approach enables us to open up the firmware development to a large group of engineers who eat, sleep, and breathe Linux. So Linux boot makes a lot of sense for us. And in short, we're turning our large pool of Linux engineering talent into firmware engineering talent, thanks to the power of open source software in firmware. Thank you.
Beautiful. We have a lot of time for questions. So, like 15 minutes for questions. Who's first? OK.
Hi. It sounds like you're basically treading exactly the right path there. Sounds really cool to see basically you were taken along the right side. I'm mostly interested in the EFI implementation part that you mentioned, because from an OS point of view, the last thing we could use is somebody who thinks they can parse grub config files and does it wrong. So what we want is we basically want to have EFI interfaces as the handover point from firmware to the OS. And you said that's partly implemented. Can you get into detail on what partly means and how far you're along and whether you need help?
So if I understood the question, you're interested about the UEFI interfaces exposed to the Linux kernel.
No, the other way around. The UEFI interfaces that you expose inside of system boot.
For running EFI binaries.
So it sounded in your presentation, it sounded as if you were working on making EFI payloads run in system boot.
Work in progress. Yeah. We currently don't have a good solution to that. This is a relatively new effort, but we do want to expand that ecosystem and try to be more compliant and open and inclusive of people that want these EFI interfaces.
Okay, so basically what I can, we should probably chat offline about this a bit, but it should be reasonably simple to actually implement it, to essentially take my code. I'm going to talk about that in a couple hours. But basically take my code, put that into a library, and use that as a wrapper, as a user space binary, and essentially just run EFI binaries as Linux user space applications then, that you can then push into a special kexec interface that would allow you to just run arbitrary Linux or arbitrary EFI binaries as Linux application, including the full boot time service state, pushing back into Linux drivers, which really is, at the end of the day, what you want for big servers, because that gets you all the speed benefits, all the open sourceness that you want, but the same interfaces as everybody else has them.
That sounds awesome. We should
So
definitely
let's
follow
discuss
up.
it later on.
Yeah.
Any more questions? One. Over there.
I'm curious about the part where you said that you have HTTPS support for the netboot, because usually when we think of netboot, we think of doing it in a local subnet that you control anyway, so you wouldn't need the security part. Are you actually netbooting payloads off the internet, or how are you doing it?
So for the HTTPS part, I guess, if I understand the question correctly, you want to know how do we handle security for certificates?
First of all, I'm asking if you are booting your netboot payloads off the internet or off some
No,
local
it's internal network.
Local network, okay. So why do you need HTTPS then? Why not just HTTP?
Because it's always good to encrypt as much as possible, as in we can trust our internal network, but I think it's reasonable not to minimize the surface of attack as much as possible. And HTTPS is not a big problem to deploy, even on firmware.
Yeah, and,
Okay.
and actually for some products like the open cellular boards, they might actually, that might be a valid use case, is you have a provider or someone hosting a bootable image on the internet, and we want to be able to download it securely to the device.
Okay, thanks.
So, are there any more questions?
Yeah, thanks for the talk. So on how many % of your systems or servers do you run this currently? So it's used active in production on all servers already, or are you still rolling this out? What's the status?
So, so for open cellular, the answer is 100%. We don't have many boards for open cellular yet. Right now, I have the 2 generations on the at our booth, and both of those use core boot and well, the first version uses CBIOS, but we're also experimenting with Linux boot on it with a modified, larger ROM. But the second generation uses Linux boot. For our infrastructure,
For servers, we don't have a broad deployment yet, but that's what we are experimenting, and that's what ideally we would like to go to.
yeah, we're still polishing up some rough edges, and the plan is to slow roll it, is what we call it. Obviously, we have a huge infrastructure, and we're not just going to switch it over all at once. It has to be staged, and that tends to take some time.
Okay, we have time for 2 more questions. Oh, Ron, thank you.
I was really interested in your comment that your boot reliability had gotten better with your system boot. Do you have numbers on that? Because I'd really like to hear them if you do.
So I don't have hard numbers because we don't have a broad enough deployment to give you to make a fair comparison. But what we see is that so far it never failed unless it was an actual service failure on the other side. All the attempts that we've done failed only not for the firmware but always for the service side.
How was it
Before, so the percentage is still small, but the number of machines, the actual number of machines can be really high in terms of hundreds of thousands that can fail. And of course, this is not something you want to tackle manually. And retries can help and alleviate, but of course, if you can eliminate the problem at its roots, it's where we want to be.
Okay, we have time for 1 more question. No questions? Okay. Oh, okay.
Aha! So do you have anything you can say about it in terms of scaling? For example, typically a single TFTP server can't actually support that many clients coming in because it's TFTP. Do you have a number for like how many simultaneous HTTPS clients you can support?
So TFTP scaling is not an issue, at least for us, and we have our own FB TFTP implementation that handles traffic quite easily. So even with a large number of machines, we can scale it a lot. But of course, when you have HTTPS, you have a shorter burst with a lot more traffic. I don't have hard numbers on how much pressure this would put on HTTP servers for us, but HTTP servers are the easy thing to scale. So even if we don't expect to be worse than what we currently have, and web servers are something that Facebook does daily. Yeah.
Okay, thank you. Please have another round of applause for David and Andrea.